Okay, we're going to continue on talking about the next topic in the series of topics that's in the handout that I gave you the other day. The handout basically includes three items, and lighting happens to be the second of the three. So here, when we talk about light, we're basically talking about, well, first of all, what is light? Light is photons. Photons propagating at a transverse electromagnetic energy wave. What does that mean? All these photons can exist and they have a certain energy level. So those energy levels can then be defined as energy packets exhibiting the properties of waves and particles. Light, unlike almost any other core substance in the universe, can be characterized with two properties, that being waves and particles. There's a whole realm of physics that talks about that. The light that we see falls under what's called the electromagnetic spectrum. And the electromagnetic spectrum is a range of frequencies of different, that are characterized by different ways, and visible light just happens to be a small portion of that. Okay? In the visible light area, or in the electromagnetic wave, we're talking about everything from radio waves, TV waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all these things that you guys may have heard about all your lives, but maybe not realize that it's all part of the same spectrum, okay? Of which visible light is as well. Each one of those wavelengths can be either long or short. They can have photons that have different levels of energy, and they can be represented as either high frequency or low frequency. Okay? As an example, UV light has a few photons, but each photon has a lot of energy. As contrasted with IR light, has a lot of photons, but each photon has less energy. That's why if you get exposed to like UV light, it becomes damaging to your skin. Okay? Because those photons actually have a lot of energy. So when we think about light, we're talking about the properties of light which there are two main property types, of that being particles and then waves, and then the characteristics which are basically isolated to the wavelength, the frequency, and then the photon intensity. And then for the wavelength can have a few different things that going on with it as well. It can be reflected, it can be refracted, it can be diffracted, or it can be dispersed. Okay? And we'll talk about a little bit of each of those. So again, when we talk about the visible light area in the electromagnetic spectrum, we're only talking about a very, very small part of that spectrum. But that gives us the range from 400 nanometers, hey, that term is coming up again, eh? Nanometers, to 700 nanometers, okay, or nanometers, however you want to say it. And that basically refers to the wavelength of each of those lights. And you can see, if you go through the color wheel, or this color spectrum, each of those have various wavelengths that's associated with the different colors as part of the visible light spectrum. At one end, you have infrared light. On the other end, you have ultraviolet light. Okay? And the reason why I point that out is because there are some cameras that have an imager chip that can recognize either IR or UV. So one of the main things that you want to be familiar with is what's called the angle of incidence and the angle of refraction. This is a physics property, and what that means is that every time you have an angle of incidence, it equals the angle of refraction, okay? When we are talking about a field of view, we defined that last time when we talked about the optical chain, right? When we were talking about the camera setup, we described the focal length, the CCD width, the field of view, and then the standoff distance, right? So if you look at this as the field of view, here we have an illustration of a camera with what's called a ring light. That ring light is actually going around the out perimeter of the lens of the camera, okay? And that creates what's called a coaxial light. Co meaning both of them are on the same axis, right? When you have a coaxial light that's going down here, you can see that there are multiple rays that's coming off that light. When those rays come off that light, each one of those rays go down and hit the field of view on the sample part or the target part, and then you have a angle of reflection. The angle of incidence is equal to the angle of reflection. If the angle of incidence and those initial angles are 45 degrees or greater, it's considered bright field. If it's 45 degrees or less, it's considered dark field. So that's where you see here these dark field areas and then this bright field area. Okay? So there are three primary lighting solutions that we're talking about, and that's inclusive of bright field, which is this in the middle, dark field, where the angle of incidence is less than, is 45 degrees or less. So the light is coming in at an angle, okay? And then backlighting, or coming in from behind the part, where you can see the silhouette. And each of those geometries have very unique ways of illuminating the target or the region of interest on a piece of sample part. So we've said the angle of incidence and the angle of reflection, both of those come and they are equal. And then we talk about the position of the light. We can have front lighting from a bright field standpoint, backlighting, and then we just described these terms here. So remember, I told you there are a lot of terms that you have to be familiar with, right? Okay. The main thing that we want to do from a lighting standpoint when we're talking about machine vision is to increase the contrast. Contrast is for grayscale. Remember, we were talking about that 8-bit contrasting mechanism the other day where we went from 0 to 255, right? And we said that each pixel on an imager chip can basically have any one of those values, but the two primary components is its location, right, and then its grayscale value. So when we enhance that 0 to 1 contrasting numbers, then we can increase the contrast or distinguish between the various features that are on there. How can we do that? These 4 items can help us to do that, and there are lighting mechanisms that help us to do that as well. Shape, texture, color, and translucency. From a shape standpoint, here we have an example of an on-axis light where the light is actually coming in, it's hitting the mirror, then bouncing back, and then going back in to create the light. And then that is a technique that can be used to highlight shapes. That's just one example, okay? For texture, here we can see that the surface of each of these two sample parts have, when you look at the macroscopic view of the surface, this one has a smooth surface, this one has more of a rough surface, and because of the way the light comes in, even if they're the same light coming in differently, the light is refracted and dispersed differently. Okay? Color. When we talk about color, it takes us back to elementary school. Remember the color wheel? We have primary colors, secondary colors. We'll talk about that as well as complementary colors and filtering, because what's happening is on this color wheel, we can manipulate the colors of the lighting source that will determine what gets highlighted and what gets low-lighted, if you will. The unique thing about this is that changing the lighting color will make features easy to extract depending on the details of the inspection. So, if we are looking at a piece of a part that needs to be inspected, and it's a certain color, you can use the same color. Say if we wanted to look at some lettering on a part, and it was a certain color. Well, if we use that same color, it can highlight it. If we use the opposite color, then we could, then it would do the opposite. It would make it go into a darker scenario. Okay? So when we're talking about complementary colors, here we have blue. I think I have a better, here we go. The opposite of red is green. These are complementary colors. Okay? The opposite of red is green. Opposite of violet being yellow, opposite of blue being orange, etc. You can see that blue, red, and yellow are the primaries. Okay? When we talk about complementary colors, here are another graphic that sort of highlights this. Red and green, blue and orange, and red and green again. From a grayscale standpoint, you can see that when you use those, they still are enabling you to be able to distinguish those features depending on which light source you use. Okay? Filtering is basically the same. Filtering allows you to either highlight a certain color or to restrict a certain range of colors. And that also is very helpful in terms of being able to determine or being able to accent, if you will, the features that you're looking for on a particular part. Okay? I'm speaking in generalities here because remember I told you the other day when we first started this discussion, when you have a machine vision problem, all of these features have to be taken into account in order to come to the correct solution. No solution is a boilerplate. So you have to go through all these different features. What we're doing is putting these tools in your tool belt so that you'll know where to go and what are some of the different possibilities that you can have when it comes to deciding your lighting sources. Okay? Color filters can be used to limit the wavelength of the light entering the camera. Then you can have polarizing filters which can prevent unnecessary light from being reflected. And then you can have protecting filters, and that's if you're in like a rough environment where you can have various types of dust or various molecules or various types of things that can be flying around or in the area of the camera and can get into it and sort of mess it up or distort the image that's created. Translucency. You all have seen a piece of glass that's sort of frosted, right? when you look through it, you can still sort of see the silhouette of the person, but you can't really tell the details. That's the translucency, which is distinguished from transparency. Okay? Lighting methods can be used to highlight the differences in translucency. A common example is the use of backlight. Okay, and that's an example of that. So the effects of various lights. When we talk about this, what I'm basically going to do is just to identify the different types of lights that you could use. This is not an exhaustive list, but it's a pretty commonly used list. Okay, and then I'll show you a chart at the end, and then we'll be done. Ring light, low angle light, dome lights, backlights, on axis light, area lights, bar lights. Okay. A ring light, the target is illuminated from a ring or light source, and it's literally what it says. It is a circular type of light, and the ring light is used for a variety of applications, and usually it's the first type of light that's used to go into a particular solution. It has a very widespread use. General surface inspection is one of its common uses. And the reason being is because it evenly illuminates the entire target. Okay? And that's important. You want to make sure that you eliminate shadows, and you want to get as much of the surface illuminated, or the region of interest that you're looking for, highlighted as best you can. And the bright field light or ring light, a lot of these lights have multiple terms, or they'll be used in different contexts. So you can see that a ring light is also a bright field. We already defined what a bright field is, so you should have that already in your mindset. Okay? Generally, we install the ring light at the end of the lens of the camera. Okay? Here's an example of it looking at a money clip. Low angle light or a dark field light, it can be a ring light source, could be used for that, but again, this is going to be dark field, so we're outside of that initial 45 degrees, right? And so it's going to, you can go to the same part and have a different impact just based on the angle of how that light is shining on it, okay? The target is illuminated at a low angle, and since unevenness in the target is illuminated, this method is suitable for inspecting flaws, for stamps on the surface, and broken contour line. And generally speaking, install a low angle light just above the target or the sample. Okay? Here's an example of that. Same scenario. You guys should have these pictures. Okay? Money clip, same scenario. We're using a dark field light, same type of light, but we just changed the angle from where it's coming. Okay? Dome light. Light is thrown or projected from the bottom up onto a dome reflector, and the reflected light is then thrown onto the target. It's one of the drawbacks for this is that it's a pretty large installation, because you actually have to enclose it within like a shroud or something to that effect, and that can become expensive. So the installation space is required around the inspection area and the inspection target. But this is another example of that, and you can see, depending on it, the target is evenly lit, and that's what dome lighting allows you to do. Backlight, the inspection target is placed between the lens and the light, and then the light is placed behind the inspection target. This is called backlighting. It's used for measuring the shape, getting dimensions, metrology. You can use it for various types of metrological methods. Inspecting foreign methods using the silhouette of the target. And it's necessary to select a plane surface of the light having an emitting surface larger than the target. And the light installation space is required on the back of the target. Okay? So that's backlight. And you can see how on this one, where the light is up here, it sort of gives you that silhouette. We're still using that money clip. Coaxial vertical light, by aligning the optical path of the light and the optical axis using a half mirror, the light is thrown vertically on the topic. And this is the one that I showed you where it says it highlights the shapes. This is a good one for that one. It's usually that the coaxial vertical light, you install that between the camera and the target. And this is an example of that. Here's the mirror. Okay. An area light, I showed you guys that, an example of that the other day where we did that LED area illuminator. But this is the same scenario where it's more of a, where it highlights an entire work area, if you will, or the area where that target or sample part happens to be. And this is what I showed you the other day, where we had an LED area illuminator going down here. We were beginning to do the initial setup for a 2D visioning process. Okay. Bar light, sort of like a spotlight in some ways, or it can be a length or an elongated bar that has lights on that, and it's thrown on the target in an oblique direction. Shiny planes on the target appear dark, and flaws and stamps appear bright. That is really cool, if you will, or unique, because just putting a illuminating device, in this particular case the bar light, on an oblique angle will change the way the little, say, the inscriptions are highlighted on an otherwise smooth or flat surface. Okay, this is a chart that sort of goes through that. I would make sure that you are familiar with some of the topics that are the different lighting types up here on the horizontal axis, and here those properties that we just talked about: shape, surface texture, color, and translucency. And there are a number of additional handouts or a number of additional examples that are pictures in your handout. But this is a good chart to give you some initial direction. Okay? And from that point, I'm going to open it up for questions, but let me stop the